Hey there, Mr. Weaver here, and this is Topic 6, Lesson 6 on compound interest. After this lesson, you need to be able to answer questions in context involving compound interest. You'll know you're successful after this lesson if you can identify and use keywords that indicate the amount of times interest is compounded, and if you can calculate compound interest. Compound interest is a special form of exponential growth, mainly dealing with bank accounts and credit cards, where interest is earned on the principal or the original amount and interest that's already accumulated. Just like exponential growth and decay, compound interest has a specific formula. It's very similar to our exponential growth formula with a few slight differences. In our formula for compound interest, three things stay the same. F of t is still your total, R still stands for the rate or the percentage, T is the amount of time that has passed. Here, time needs to be in years. We also have P. P stands for the principal or your start amount. It's pretty much the same as A was in our other values. It's where we're starting. In compound interest, though, we do have a new variable, and that is N. N shows up twice in the formula, and N stands for the number of times compounded in a year. So in the problem, it will tell you that the interest was compounded, and it will give you a certain word that tells you what number to plug in for N. So here are some common words that will tell you how many times interest was compounded. It's probably not going to come right out and say that interest was compounded 4 times this year. It's going to use a different word. So if you see yearly or annually, that means that interest was compounded 1 time in a year. You probably won't see these two very often because using 1 doesn't change much, but just in case. If you see semi-annually or biannually, that means it was compounded twice in a year. Quarterly would mean 4 times in a year. Monthly, 12 times. Weekly, 52. And daily, 365. Again, these tell you how many times that thing happened in a year. Let's look at an example of calculating our compound interest and calculating how long it would take to get to a certain point. And again, like we did with exponential growth or decay, we can use Desmos. Kimberly's family invested in a certificate of deposit, CD, of $3,000 for her when she was born. The annual interest of 8% is compounded quarterly. What is the value of the CD after 5 years? Here's our original formula. We need 4 things: the principal, the rate, the time, and the times that it was compounded. So principal is where we started. She started at $3,000. Our rate is 8%. The time is going to be 5 years. And N, the number of times compounded in a year. So we can see the word compounded. And quarterly tells us 4 times. If we plug in those values, 3,000 was our principal, times 1 plus 0.08, our 8% as a decimal, divided by 4, parentheses, and then 4 times 5 in the exponent. So that 4 shows up twice. Now we can just type it in a calculator and figure out what that equals. You can always simplify the fraction first by dividing it out. So 0.08 divided by 4 would be 0.02. And then 4 times 5 for our exponent would be 20. So if that's easier for you to type in, then simplify it first. When we calculate it out, we get $4,457.84. So that would be her value after 5 years. How long would it take for her CD to double in value? For this, we're going to need the help of Desmos because if it's asking how long, we need to figure out the time. And again, we don't know how to solve for an exponent yet. So here I'm going to take the same, except instead of 5, I'm going to plug in t. And if we wanted to double, it would start at 3,000. Doubling would be at 6,000. So I want to know when it's equal to 6,000. In Desmos, if I type in my function, instead of t, I put in x, but everything else I just typed in, making it look like what it should in the formula. So principal of 3,000, rate of 0.08, n was equal to 4. I don't know my time, so x is going to be equal to t. If we try to use t in Desmos, it doesn't work quite right. Now, I want to know when my total equals 6,000. So just like we did with exponential growth and exponential decay, I'm going to zoom out until I can find my spot where my two lines cross, and then I'll zoom back in. So my function and my total intersect at 8.75. And since we're solving for x, that first number will tell us how much time has passed. So 8.75 years. So the time that it takes is 8.75 years. That's how long she would need to leave it in order for it to double in value. Now it's your turn. Pause the video, read through the situation, see if you can figure out what Joshua's balance is in 8 years, and then use Desmos to see how long it would take for his account to double in value. Let's check. After 8 years, Joshua's balance is $922.18, and it would take him 9.059 years for it to double in value. Let's check how to get there, starting with our formula, and again what each variable represents. So 500 is where we started, rate 7.8, semi-annual, so n should be equal to 2, and for 8 years. Plug those all in. Make sure your rate for 7.8% is 0.078. You still would need to change that to a decimal by moving the decimal point twice or dividing it by 100. Just because there's a decimal point in the percentage does not make it a decimal. Plugging all those values in, you should have got 922.18. And then to make it double, we use the same thing again, except instead of plugging in 8 for our time, we use t, or in Desmos, we use x. Set it equal to 1,000. You should find the intersection point is at 9.059 and 1,000. In this lesson, we learned that compound interest is just a specific type of exponential growth where our total amount of money is growing based on the original amount, but also interest along the way. In these problems, in context, you're going to look for the word compounded, and that will tell you how many times your interest is recalculated in a year. So for example, compounded quarterly would mean the interest is re-added 4 times over a year. So n would be equal to 4. This formula can be real useful in real life, as the number of times that interest is compounded is just as important to consider when you're finding a loan or a bank account as the interest rate. As you increase both values, so both the number of times you compound it and your interest rate, your total is going to increase faster, which is great if it's a bank account and you're saving money and it's increasing, or that could be bad if it was a credit card or you're paying back a loan and that interest just keeps going up faster and faster, making more that you have to pay back. So knowing about this is very helpful in considering some of your future financial situations. After this lesson, do you now know how to identify and use keywords that indicate the amount of times that our interest was compounded? And do you know how to calculate compound interest? If you're not sure about these things, go back and look at our 2 examples, see where numbers fit in, and how we can calculate out our compound interest. And that's the end of lesson 6 on compound interest.